recorded meetings.
Can.
Okay, so we start recording now.
Yep. Hold on. Can you see the slides on the screen? Yeah, so today I'll be talking about object detection with fast RCN. Actually, I guess to explain this paper in more detail, I actually be going through not only fast RCN, but rather the entire RCN family of models. And the structure of the presentation will be more like a walk through the entire history of RCN family models, from RCN all the way to faster RCN, and I'll motivate some of the like architectural decisions that the authors made to improve both accuracy and also even speed of object detection models. Yeah, so first off, let's just let me just explain what object detection is. So I'm sure most of you are already familiar with what image classification is, where we just assume that there's one main target in the image, and the model's sole focus is to identify the target category. Right. So for example, in this image, we just want the model to take in this image and then output, let's say, a probability vector, right, of what is an image. Like for example, in this case, we want the model to output a high probability value that there's a cat in this image. But in many situations, there are multiple targets in the image that we're interested in. So not only do we want to classify them, but we also want to obtain their specific positions in the image. And we refer to this kind of task as object detection. So for example, in this image, we have there are multiple objects of interest, such as we have 2 dogs and a cat. So what we want the model to do is to both localize these objects and classify them. So in technical terms, this means that we want to feed the image of the model and have it output 3 bounding boxes. And in terms of numbers, like a few ways to represent, maybe one way to represent a bounding box might be, let's say we just output the coordinates of the center of the bounding box and also the height and width of the bounding box, right? So we do this for each bounding box, and for each bounding box, we also want the class of that bounding box. Okay, so it kind of looks like this, where so we want the model to, let's say, output like a certain number of probability vectors. So in this case, since our image has 2 objects, we want our model to output two vectors. So where each vector is, the probability of the class, and then 4 more numbers that defines a bounding box, right? So this X and Y could be either like the upper left point of the bounding box, or it could be the center of the bounding box, and also the height and width of the bounding box, right?
Okay.
Yeah, and then so obviously this is a more challenging task because it requires both successful localization as well as, on top of that, you have to create the correct class of the thing that you've localized, right? And maybe one more thing is also, like, if you notice, each image actually requires a different number of outputs, right? So unlike traditional deep learning, or rather machine learning models in general, our inputs, outputs are kind of fixed. But in the case of object detection, because each image can have an arbitrary number of objects, the model needs to also output an arbitrary number of bounding boxes.
Yeah, because there's no predefined number how many objects are there in the images. So probably only 1 object, they probably have 10 images, right? So the output is more, the number of objects is just dynamic on the runtime.
Right, yeah. Okay, so how do we perform this object detection? So I'll just first start off with introducing the so-called the general object detection framework. So I won't actually go into the technical details first, like the architectural details. Instead, I will first give a very high-level overview of so a high-level overview of how different object detection systems approach this task. And typically, like for most object detection frameworks, these are the 4 steps that are required. So in this order, we will first, right, so I'll just go through each step one by one. Yep. So first of all is region proposals. So what the technique that most models have converged on is, we don't want to directly output this, we don't want to directly classify, we don't want to directly output boundary boxes and classify those boundary boxes. What we can do instead is have a kind of a pre-processing step where we first output instead boundary boxes where we think there's the object, right? So we will have the network output multiple boundary boxes and give each of them a so-called objectness score. So instead of predicting the class, we just predict whether there's object in the image. Right, so we call these regions of interest. And they're just like regions where the model thinks that there's a high likelihood that it contains the object.
Okay.
Yep. So one point to note is, in this step, like at least for RCN models, it actually produces like thousands of boundary boxes, thousands of regions of interest to be further analyzed and classified by network. Yeah, so for this step, as I said, it actually comes out of thousands of candidates of regions of interest. So it will only select those boxes with high objectness scores to be selected for further processing down this object detection pipeline. So in a way, this also introduces another threshold that you can configure. So in this case, it'll be, not sure what it's called, but you can configure a threshold to determine how many boundary boxes that you want to carry on to the next step in the pipeline. Yeah, so now that we have these, candidate boxes, our regions of interest, what you can do next is, for each boundary box, we just classify that boundary box, right? So in a way, you can see this as, we are just treating our object detection task as an image classification task, where we first have this pre-processing step where we crop out regions in the image where we think there's an object. Then we pass that crop image. We just pass that crop image into a, like an image classifier, for example. Yeah. So what's normally done here is this visual features extraction module is typically some pre-trained convolutional neural network. Right, so you can just pick your favorite, CN, like ResNet, VGG, or whatever. So the point is you want to extract high-level features from this image, right? Which is what a CNN does. And now that we've extracted these features, we can finally just pass it to a prediction network. So this can just be another neural network to finally output the numbers we want, which are the boundary box coordinates and also the class of the boundary box. Right. So for example, in this case, let's say after this step, we have proposed all these regions of interest, right? And then we've filtered only these 3 boundary boxes that has high objectness scores. And then in this step, we will pass both these 3 crops of the image into a pre-trained network to extract the features. And then finally, we will classify each of these regions of interest with all these numbers. Yeah. So one thing to notice here is there's multiple overlapping boxes, right? Which is actually typically what happens after the region proposal step. Is that you propose a lot of regions and most of it will overlap with your object of interest. But this is not what we want, right? We only want one bounding box on our object of interest. So what typically happens in most object detection models is a non-maximum suppression step. So what this method does is basically it just tries to combine overlapping boxes into a single bounding box, right, for each object. And if I'm not wrong, most object detection algorithms use this same technique to combine these overlapping bounding boxes.
Yeah, I think YOLO somehow is somehow different, but this is a two-stage model. Let me keep going on. I have some questions for the training process and the back propagation.
Oh, sure.
And anyway, I just raise my questions later. We can keep going on. I think as far as for now, I think your explanation is quite clear.
Right, thanks. Yeah, so maybe just a brief, a quick overview of how this algorithm works.
So if anyone would have a question, you can just raise it as me. So I think Yizhe will be happy to answer it.
Yep. Yeah, so how this algorithm works is basically these few steps. So we'll first just discard all boxes with we're not very confident of, right? So less than a certain confidence threshold. And within the remaining boxes, we will, so this is a greedy algorithm. So from step 2 onwards, we will select the highest probability box first. No, our most confident bounding box. So let's say maybe in this example, this might be the bounding box where
0.9.
Yeah, 0.99 score. There's a cap. So we'll then discard, right? So actually so those boxes with high overlap, we'll just combine them, right? So in this example, it'll be these two bounding boxes that has a very high overlap with the bounding box that we're considering, our most confident bounding box. And we'll just average both the scores and also the bounding box positions together. And then those with low overlap, maybe just overlapping 50% with our most confident bounding box, we just throw away. Right, so that's where the name comes from, right? We will suppress those low confidence bounding boxes. And then finally, we just repeat from step 2 again, right? So from the remaining bounding boxes, so excluding the most confident box that we've considered and also those we've thrown away, we then select again our second most confident bounding box among the remaining bounding boxes. Right, so we just keep continuing this process until there's no more candidate boxes left. Right, so that's non-maximum suppression. So what we hope from this, yeah, sure.
So here, you select the highest probability, the box with the highest probability, and then also average the boxes with the high overlap, right?
Correct.
Then after the overlap, how many boxes left?
Oh, so only one.
Only one. Then
yeah,
how do you repeat from 2?
Also, so actually there's actually at this step it maybe look more like
sorry,
this.
I have small questions for the predicting the same class average together. So
yeah, sorry. So I forgot to mention that it only consider the same class. Yeah.
Yeah, the same class. So suppose there
Right.
in your case, there is one box with highest one, suppose is 0.9, and the other two box overlapped with highly overlapped with 0.7 or 0.8. What do you mean by average together?
Also average.
Yeah,
so
what does average mean?
Positions, but actually I'm not sure whether it averages the confidence scores or not.
So basically, as long as it is kind of with a high confidence or with a high score, you can just get rid of it. Why we need an operation of average?
Oh yeah, I think there's multiple variations of this algorithm. So I think some just skip this step.
Okay.
So some just discard those with, so some just discard those with, some just discard the high overlap boxes, yeah. And also the partial overlap boxes.
I think the average is to average the boundaries, right?
Okay,
Boundaries. Of
Yeah, so you average the X,
yeah.
Y.
Yeah, for example, there's two bounding blocks, one 0.99, the other is 0. Maybe still 99. So maybe they actually break the tie because the confidence or the score was 0.99 and 0.98. As a matter of fact, they actually make no fundamental difference. So in this case, they actually just every bounding box have a vote. So they average all the bounding box to adjust it in the middle. Idea is that maybe the final bounding box this will be like this. Can you see my yeah, maybe I'm using the yellow one. Yeah, the final bounding box maybe looks like this. It's really yellow one. So that was so anyway. There's a trade-off for the final bounding box here, right?
Yep.
Okay.
So my question is that after average, the bounding box left is 1, right?
Yes.
Then how do you repeat from to the fifth step?
So typically there's multiple objects in the image, right? So you have
okay.
like 3 bounding boxes like on this cat, maybe 5 other bounding boxes like on this dog.
Okay, I see.
So like even after this step, there will be bounding boxes left. They are not suppressed. Yeah. Yep. So that's non-maximum suppression. So after this step, you will basically already have your output, final output. Right. So one last thing I'll go through in this framework are the evaluation metrics. So for object detection models, these are the 2 main evaluation metrics. So we have frame per second to measure the inference speed, and then mean average precision to measure the performance of the network. Yeah. So for example, like this table comes from the Papers with Code website. So if you don't know, this is just a website that like helps to like consolidate a leaderboard of the best performing models out there that actually have reproducible code. Yeah. So these results have been reproduced in their code. So as you can see, yeah. So actually, this is the leaderboard of the best performing real-time object detectors. So you can see we have like progressed quite far from the typical classical models such as RetinaNet or YOLO to all these models with all sorts of names. Yeah.
So YOLO is actually the most efficient way, but in terms of accuracy, they have to compromise on the accuracy, right?
Yeah, correct.
Let me check about the. Let me look at it the website. So how do they rank all the methods? So based on what do they rank? So the efficient D7 is actually the most accuracy, right? It's just based on accuracy.
Yeah, so this is leaderboard for real-time object detection. So I think they only consider models with, let's say, I don't know.
So where is fast RCN? Where is the fast RCN?
So fast RCN, I guess they don't consider it to be real-time. So I guess for real-time, you just have to go to search object detection.
So it should be, so the fast RCN is supposed to be
this. As you can see, there's a lot more exotic models out there. Faster RCN is.
It's not a state-of-the-art model anymore.
Yeah.
Okay. Anyway, I think the idea or concept are the same. Maybe we can investigate more object detection algorithms ourselves. Let's keep going on. So anyway, there are 2 metrics. One is for the sufficiency and one is for the accuracy. Yeah. But anyway, for the state of the website actually ranks these methods in terms of accuracy, the mean average precision. Please go on.
So actually, hold on. Yeah, so there's two metrics. So I guess FPS is quite intuitive to understand. It's just number of frames it can do inference on per second. So for mean average precision, before I go into it, I'll just explain like two more metrics that actually make up this metric, which is the IOU and also the mean, and also the precision and recall curves. So IOU is just a measure of overlap between two bounding boxes. So this measure is actually already been used in the previous step. Like for example, when I say high overlap or low overlap, they typically use this IOU metric. Okay. So yeah, to calculate IOU is just you take two bounding boxes, you take the area of the overlap, and then you divide by the area of the union between the overlaps. Yeah. So this metric ranges from 0 to 1, where 0 is just completely no overlap. And then 1 is they have perfect overlap. So not only do they overlap, but they also, not only do they overlap completely, they also are of the same size and height. Yeah. So yeah, so this metric is important for evaluating the accuracy of object detection because, like let's say, so because to do even to do training or to do evaluation, you have to kind of match between your predicted bounding box and the ground truth bounding box, right? For example, let's say you predict this bounding box, and then the ground truth is maybe somewhere over here. So to what extent
the basic idea is that IOU is a very important metric to calculate the loss. Suppose the bounding box is not perfectly predicted, and how to adjust the bounding box using the neural network model.
So basically, how much benefit of doubt do you want to give your model? So again, we have to set another parameter here, which is the IOU threshold. So for example, if we set it as maybe 0.5, we kind of say that as long as our predicted bounding box has an IOU of 0.5 with the ground truth bounding box, we will say that our model works. Our model has predicted that bounding box. And of course, you can set a more stricter threshold, let's say 0.9, so that.
So what is the average standard of the IOU threshold? 0.9 or 0.5?
So for at least for COCO evaluation, it will do. So you actually do an average of IOUs from 50 to 90 or 95. So actually this metric over here is average of the metric considered over thresholds from 0.5 to 0.9. Yeah, so this is a rather strict metric.
Yeah, it is quite rough. Yeah, so 0.5 to 0.9, all the possibilities are there.
Yeah. And so as opposed to this other two metrics over here. So AP50 just means we consider the accuracy with IOU of 0.5. And then this is with IOU of 0.75. So you can see as the IOU increases, it's a more stricter metric.
Yeah, the MAP actually increase as well.
Yeah, so the AP will naturally decrease.
So there's no standard. But anyway, when they compare with different models, they can just set a unified threshold. Their model just perform on this threshold.
Yeah, so the point of this IOU metric is to find out whether a detection is correct. Yeah, so to find out our true positives and our false positive. Yeah, so if our predicted bounding box has a high overlap with the ground truth bounding box, we will label it as a true positive, right? And yeah, so if it doesn't have a high overlap, we'll just say that it's a false positive. You know, it's predicted, it's localized the object wrongly.
Okay.
So this metric is to identify both true positives, false positive, and also false negatives. So because after computing all your true positives, false positive, and false negatives, then you can finally calculate both the precision and recall of our model. So if you've done like classification tasks before, like these two metrics should be familiar to you. So I guess in a way, like precision is like a measure of how often does your, like when your model predicts, does it predict correctly or not, right? So the denominator is actually like all your, the counts of like the total number of bounding boxes is predicted, right? So all your positives, all your predicted bounding boxes. So out of all your predicted bounding boxes, how many do we actually get it right? So that's the precision. And then recall, on the other hand, is out of all the ground truth bounding boxes, right? So that's why the denominator is false positives plus false negatives. And so out of all the actual bounding boxes, how many do you actually get it right? So that's the recall. And to like typically to evaluate like binary classification tasks, we will use this, like we'll plot this precision recall curve to determine its performance. So how you plot this is basically you will vary your confidence threshold, right? Yeah, so basically this plot is, so inevitably there's like a trade-off between precision and recall, right? Like, for example, as you predict more, bounding boxes, let's say you set your confidence threshold to be very low, and you just like try to predict as many objects as you can. Then obviously you will eventually, you'll cover all the ground truth bounding boxes, right? But then you will actually get a lesser precision score, right? Because you are predicting a lot of bounding boxes, but of course you're not going to get most of them right because you're lowering your confidence threshold. So this precision recall curve is just, you vary your confidence threshold and then you plot the precision and recall that you compute for each confidence threshold. And yeah, so the average precision is just the area under the curve. And so this area under the curve is it's also standard metric for classification tasks, right? So it kind of tries to measure the yeah, so we want like as high as, like we want the area under the curve to be as high as possible. Because
yeah, that's still also called AUC curve.
Yeah, correct. Yeah. So you will compute this average precision or AUC for each class, right? So you actually plot this curve for each class, and yeah, so you compute the average precision for each class, and finally the mean average precision is just the mean of all these average precisions. So you just calculate, you just take the average precision over all your different classes. Okay, so like maybe just to recap a bit. So, each bounding box will have an objectness score associated with it. So, before that, we first choose an RU threshold, right? So how much benefit of doubt we want to give our model. And then for each class, we have our bounding boxes and also the property scores for each class. We will calculate the precision recall from the RU threshold that we define. And then from that, we will plot the precision recall curve and then calculate the average precision. So after we've done that for each class, we will then average that and finally get our average AP.
Okay, I suggest that I think Yizhe actually did a very good job to explain what is MAP. And now some of you have understand it, but some of you may not understand. I think these are very basic concepts. I think Yizhe take a slow pace and then to clarify every concept. So maybe I suggest if you have a question, just raise it. But anyway, this is very, very important concepts for object detections. Almost all the object detection algorithms actually are comparing based on these kind of metrics. What is precision, what is recall, what is IOU, and what is AP, and what is MAP. So anyway, that is very important concepts. So maybe Yizhe can just be summarize a little bit, then you keep going on.
Yeah, I can. Yeah. So I guess I didn't really explain this like concept properly, but yeah, I guess you can read this out on your own. Like it's a standard classification metric for binary classification. Yeah.
Okay. Oh, okay. Yeah, let's keep going on. Let's go into the topics of RCN. So I'm actually kind of have some curious about the backpropagation algorithms here.
Oh, sure. Yeah, so like finally so after introducing like general framework, I will finally delve into the actual technical details of each architecture. So like the model that started off this is the RCN model. Yeah, so I explained in a bit why it's called, why is it called this way, region-based convolutional neural network. Yeah, so like I mentioned before, the first step in any object detection model is to do this region proposal step, right? And the algorithm that's used in this, like this first RCN paper is actually something called the selective search algorithm. But I wouldn't actually go into detail of what this algorithm is. You can just treat it as like a black box, right? It's just some algorithm that looks at a picture. It tries to find, it kind of tries to find like what are the blobbly patches in the image, and then classify them as regions of interest. So it's like a very classical algorithm that tries to extract regions of interest, like regions in the image where it thinks there's an object. Yeah, so that's the first step. And then the second step is, we've identified this region of interest. So we'll crop them. And then, because in the olden days, like ConvNets can't actually, it actually has to have a fixed input size. So what typically happens between, like after extracting the region of interest is we will kind of pull this, like we try to resize it into a fixed size before feeding it into our visual feature extractor, which is just some pre-trained content, right? So for each region of interest, we will try to classify it using pre-trained content. So for each region of interest, we feed it into the ConvNet, and then finally, so at this step, we will have like feature maps for each image. So you can think of it as like a tensor where that basically try to detect like all sorts of features in the image, right? And finally, after this step is to perform your classification and then bounding box regression, right? So using the extractor features, so what RCN did is just like, you feed it into some classical machine learning algorithm. So in this case, you just use SVMs, super vector machines. And then you also pass it into another model to perform regression.
SVM. So basically, you mean the classification is using SVM to do the classification?
Right. Yeah, so you can imagine it's not very efficient. So if I'm not wrong, SVMs unit.
Why do you use SVM to do the classification? You can just using the sigmoid or using an approach to do the.
All right, I guess back then it's not that obvious or something. Yeah, so they just. Yeah, I guess it's like
published on 2015, right?
I think 14.
14.
Because I think back then, like in traditional.
Okay. So faster season is proposing in 15.
Yeah, like next year. Yeah, following year. So you get these features, you just classify them. So perform both a classification task and a regression task.
Mm.
So for the body box, it's a regression task because you're predicting numbers, right? Yeah. So the kind of like the optimization process kind of looks like this, where you have these two models to train, basically. So what you do for every image is
Hello.
Yeah.
I have a question. So what is the output from ConvNet? Is a feature vector or feature map?
Feature maps. So yeah. So yeah, I think this is the CNN explainer that someone's supposed to have a paper presentation on. And so like this website is pretty cool, you all should check it out. But basically, yeah, so this feature map.
Then you have to flatten it in order to do SVM.
Okay, so for CNN, yeah, I suppose so. Yeah. Flatten it. Flatten the feature map.
Okay. Thank you.
What do you mean by bounding box regression?
Right, so you can just think of it as like any kind of regression problem where you take an input, then you output 4 numbers. Because to define the bounding box, you just need 4 numbers, which is, let's say, like just the coordinates of the center of the bounding box and then also the height of the bounding box. So you predict these 4 numbers.
But when you select the region to input to the CNN, you already have a bounding box, right?
Oh, yeah. So and so in a way, this bounding box regression part over here is trying to extract, like, I guess trying to refine the initial region proposal.
Okay.
And so on top of, so on top of like, extracting from the image, you just do one final regression of where you think the bounding box actually is based on these features.
Okay.
Yeah, so that is the ASEAN model. So you can see this. So if you're familiar with like modern deep learning, obviously there's quite a lot of problems with this model. Like at first glance, there's a lot of inefficiencies. So for example, as you can see in this image, like for each image, we actually have to pass in all our regions of interest into a ConvNet. Like I mentioned earlier, that typically like this selective search algorithm will propose like thousands of RIs. And what you have to do next is you will attempt to classify each of these RIs. So you'll be performing like 2,000 forward passes on the ConvNet, which is really not very efficient. So ASEAN has very slow inference. And furthermore, like there's a lot going on, right? So, because like the trend in like most deep learning algorithms is more of like an end-to-end pipeline. But for this ASEAN, as you can see, there's many, like it's a very multi-stage pipeline with a lot of models that has to be trained separately. So first of all, you have this selective search algorithm that is like totally separate. Like it's not even a machine algorithm, it's just a fixed algorithm. And then you also have like a ConvNet, and then finally 2 separate classical machine learning algorithms that does your regression and classification tasks. So for optimization, it's actually very complicated, where what actually have to do is, yes, for each image, you will actually have to keep in memory all these feature vectors that you have produced, and then perform your SVM training, for example. Right, so that is very inefficient in terms of both memory and time. Yeah.
And the ConvNet is also fixed, right? The ConvNet.
You can you train it?
The ConvNet, I think the Basically, if you just fix the number of the categories, you can just using the ConfNet to train it, right? So it can pre-train. Basically, the ConfNet can pre-train. I think that the challenge here is that how to train the bounding box, right? The bounding box regression. I think that is most challenging part here.
Yeah.
As long as the bounding box is correct, and you are using a ConfNet, so actually, why you are using SVM here? It's very likely that the ConfNet is a pre-trained model.
Yep.
So why we need to enhance the SVM model to further quantify the feature maps?
Oh, sorry?
I'm saying that the ConfNet is very likely to be a pre-trained model. So when you are having a correct version of when you have a correct version of bounding box, you're using the ConfNet, then the ConfNet will output a feature map. So as long as if the ConfNet is trained during the object detection training process, there's no need for SVM, right? So only if the ConfNet is pre-trained, if the SVM model is useful.
Yeah. Yep. So I guess like at this point, there's quite a lot of obvious like improvements you can make. Like for example, yeah. So I'll get to them in the next model, which is published by the same guy in the following year, which is the fast RCNet. So like the main innovation in this paper is instead of first running your region proposal and then running those proposals through a ConfNet, you'll flip these two steps, right? So instead of running region proposal first, you will actually run your ConfNet through the image first, right? So the benefit of this is you only have to run your ConfNet once, right? Yeah. So previously in RCN, you will crop the image. So what you do in fast RCN instead is you will crop the feature maps.
Yeah, somehow similar to YOLO, right? Okay, please go on.
Because really the feature maps, like they still contain spatial information. So really you can just run your ConfNet through the image and then just select your regions afterwards. Right, so they have flipped this two steps. And yeah, so after the feature extractor, they still run the same selective search algorithm to find blobs in the feature map. And then after cropping out those features, you will again finally perform your final regression and classification task. So I think in this case, they do away with all the classical ML algorithms and just put a new network instead. So this way is better because it can.
I just have a feeling that the original RCN should be called a slow RCN, and the fast RCN should be called a normal RCN, right?
Yeah, it's actually like magnitudes of all those magnitudes faster.
Yeah.
Actually, I think instead of fully connected layers, it uses doesn't. Yeah, but yeah. So
hello, I have a question. So here you will have a feature map.
Correct.
Then you do the RLL pooling. Then
Yes.
you will get a fully connected feature vector for each of the feature map. Then after that, you concatenate them, or you do the softmax classifier and regressor separately. So for each feature vector, you will have a.
Oh, so okay, I'm not sure like in the original paper what is done over here, but like the more obvious thing to do is instead of using fully connected layers, you'll just put CNNs on top of this. So you put more convolutional layers on top of these feature maps to finally output these two values.
My still questions here. So I think we should speed up the process because Zhangcheng is going to present as well. So the idea is that giving a, I'm sorry, I just change the color. So given a reported region, so that actually is do a selective search where you have a region that are there is traditional approach, right? The selective search is the traditional approach.
Yeah.
The traditional approach apart from the modified feature maps. Then we supposed to have the which supposed to have the I mean the classifiers. So I think they should share the same. I think anyway. Somehow there should be an independent. There should somehow an independent classifier, even if it's a neural network model, right? So each region will connect to so this FC is actually an independent classifier. So once giving a proposed regions, actually kind of fixed regions, and these classifiers output not only the softmax classifiers, but also the region. So the fully connected network actually output five variables or five outputs or five predictions.
Yeah, actually, I mean, it depends on like, you can have two separate networks, or like you can have, yeah, so you can either have two separate networks, or you can just share some computation first. So you pass it through more computational layers first, and then finally split into these two tasks. So I guess it's just it's an architectural decision to make. But I'm not sure what exactly the authors did.
Okay, so I think we should somehow split up a little bit. I think we should finish this presentation within 15 minutes.
Yeah, sure. So so even with, so this is fast RTN. So even fast RTN, sorry. So it's supposed to be this slide. Yeah. So even with, so it actually increases inference time by quite a lot. But even so, there's one final bottleneck, which is our selective search algorithm.
So the bottleneck is actually the efficiency bottleneck, right? It's not an accuracy for efficiency.
Yeah.
Okay.
Yeah, so like really the final step to actually achieve a complete end-to-end model is to find a way to replace this with a neural network, right? Because really with, if we manage to make this entire thing a neural network, we can just train it. We can just perform a single optimization procedure and train all these weights in tandem, right? And also you're making our selective search algorithm learnable, right? So so right now our selective search algorithm is actually fixed. You can't really change it when your task changes. So what would be better instead is, just replace this with a neural network and then learn it with the rest of the model and also with your data set. Yep. So that's how we get into faster RCN, where we will completely do away with the selective search algorithm and make it into a neural network. So how that works out is, so instead of the selective search algorithm, we will use a neural network. So we'll pass these feature maps into another neural network to predict these regions of interest. Because our regions of interest is really, basically our selective search algorithm is like another object detection task, right? Where instead of predicting the classes, we're just predicting whether there's an object or not. Okay, so we have a separate neural network here that performs object detection, so-called, but on your outputs whether there's object or not, right? You're just trying to select your candidate bounding boxes. So then after this, it's just the same now, where the proceeding steps is just a fast RTN, where you're passing these crop feature maps into the same network, same kind of network. Yeah.
Okay, that's good. Okay, so the basic idea is that, sorry, so we go back to the previous slides.
Yep.
So anyway, so you have a feature map and extraction. So for each region, so how do we know if we're going to select it, if we're going to select it as our region of interest, if we're going to propose a region of interest, so we still have some label, right? So
Yes.
So how do we, anyway, so how do we know this feature map, these areas is supposed to be the an ROI, the region of interest.
So so this network is also trained. So you also have to have your RI labels.
RI labels.
So I think it's very similar to what is done over here, where you define some RU threshold. So you will, like how you assign your predictions to your ground truth is, like if there's a high RU, then you just assume that.
Yeah, anyway, so when you are outputted a feature map, so how do you know which region of the feature map is actually and how do we correspond to region? How do we correspond to the label? Right. So this is one region object.
So do you mean how do we
label? How do we label? How do you correspond to? How do you calculate the loss? Hello.
Yes.
Yeah. So this is the input, and this is
right.
This is an output, right? This is an output, and for this output, there actually have one loss here and I have one loss here, right? Here's the L1 and L2, right?
Yep.
So anyway, this is feature map. How do we correspond to it? Or I think the final output will have the same size of the original one.
Oh, okay. So yeah. So actually, I think I have some further slides on that. Hold on now. Yeah. So so I'll go in more detail of how the region proposal network actually works. So what it does is, you can think of it as you're separating an image into a grid, right? And then what the RPN does is, for each grid, it will predict whether there's an object in that grid.
Yeah. So anyway, so I guess you divided images into a set of grade. So every grade will every grade will corresponding to the final feature map, and then each grade will correspond to whether it will contain an object, right?
Yeah. Because if like think of what a CNN does is, for example, like let's say in this last layer, we have a feature map like this, and what it's doing is, so let's say if a region is activated, it's saying that there's some feature, there's a high presence of that feature at this portion of the image, for example. And as you pass your image further down in this CNN layers, like each pixel over here has a certain receptive field of the original image, right? So like something like this now, where as you pass your CNN filter, each pixel of your resulting feature map has a certain receptive field, and as you pass in your network through multiple layers, the receptive field increases in size. So you can think of one pixel of the feature map as corresponding to some part of the feature,
part I understand.
some part of the image. Yeah. So one additional detail is, it doesn't actually, so for this RPN, it doesn't actually predict the height and width directly. It actually predicts offsets. So, because I think like from experience, it has like found out that it's actually very hard to predict, like for example, the center coordinates and also the height and width directly. So what I thought of doing is to define so-called your prior bounding boxes first. So for each of one of these grids, we will define anchor boxes. So these are just like your fixed prior bounding boxes that the network will use as a reference bounding box for your final prediction. So instead of predicting the specific X, Y, WH, you just predict the deltas, like the offsets from your prior boxes, your anchor boxes. So for example, I think for fast RCN, it has 9 anchor boxes for each grid. Yeah.
Okay, please go on.
Yeah, so again, so what happens here is for each pixel, it will predict. So for each pixel of the pixel, for each pixel of feature map, it will predict 9 bounding boxes, right? Because we started off with K anchor boxes. So actually predict like 9 bounding boxes for each image.
Okay. Okay. Yeah, I think here it's very clear now. So Yizhe, you can just speed up a little bit.
Yeah, sure. So in terms of optimization, is just, you have a neural network over here that has these 2 outputs. If you have a neural network over here, then you just.
So for this network, only the object only the grade, which is predicted to be the object, will be feeding to the final loss, right?
Right. Yeah.
So anyway, so here it's either 1 or 0, right? It will be either
yes.
1 or 0.
Right.
So anyway, so this is softmax, whatever it's softmax. So does that mean that whether the grade, which is predicted to be an object, will be used to calculate, will be used to predict the class, or it is? But I see there's still connection here.
So this actually this will be like 2 separate. You can think of them as 2 separate optimizations going on.
But they actually, when trained, they're only one neural network model, right? Only one network.
Yeah.
Yeah. So basically, if they train it, all the laws will be placed together, will be summed up together, and to do the training, to do the propagation. So anyway, so despite there's 2 different optimization objectives, but anyway, they will turn multiple objectives into single objective by stand up them together.
Yeah.
So another question is that why they will have to do the regression for twice?
Maybe it's like one reason why 2-stage detectors work better, because you can think of like this final step as like your bounding box refinement. So you just come up with a proposal first, then it will still perform a final refinement step on this bounding box coordinates.
Refinement. Yeah, so I see. I think the difference lies in, for example, if there's an object like a traffic light, another object is pedestrian. So if you're going to find a bounding box here, this part may be not so accurate because different objects may have different size. But for here, it will actually predicting the bounding box for different class, right? Maybe somehow.
Yeah.
This may be the reason
kind of
for doing this. Okay, please go on. So we do really need to speed up because Zhangcheng is waiting, and I think the other people, I think they're not so strongly involved, but we still need to update it a little bit.
Yes, right. So yeah, so for like this final faster RCN model, there's actually accuracy gains, and obviously very like orders of magnitude of gains in inference speed. So like this is the initial RCN to fast RCN and then to fast RCN. Yeah.
Okay. So
I guess I'll just end off with maybe discussing some of even the limitations of this family of models. So I think even so, it's not a true real-time object detector because it's performed in 2 stages. It can't be real-time. And then also like the training process is actually not as simple as it is, because like as I've put on the slide, there's actually 4 losses. And like basically we are framing it as a multitask problem.
So when you are doing the propagation, you add all the loss together, right?
I think, so I haven't looked in details, but I think in initial paper, they like do like a warm up of this. So they kind of train this first. You train RPN first to warm it up, and then you kind of then train together.
Okay.
Yeah. Yeah, so multitask training is tricky because, like, as I mentioned, like you have to come up with more decisions of, let's say, how to, like, whether should we train this first or should we train together, and also how to balance the different losses, and also if think about whether training this task will like hinder the other task, right? So like there's a problem with multitask training in general. Yeah, so that's why people have come up with single stage architectures such as SD and YOLO, which are different kinds of models that can actually do real-time object detection, but I don't think they still can't match the performance of Sutich architectures, I think. Yeah.
Okay. Okay, thank you. I think that's one of the comments is that the RCN is actually a very classical algorithm. So when we compare YOLO to mention RCN, so yeah, I think we can still stick to the YOLOs, but we still need to see the effects of how the RCN perform to training the logo. Okay, that's cool. Is there
I have a question.
Okay.
How do you define a real-time object detect?
Fast, I think it should be the frame per second. So the fast RCN can only process maybe 6 or 9, 6 less than 10 frames every second. So it will be far less efficient than the YOLO. I think YOLO will be past maybe 40 to 50 frames per second. So it cannot be used as a video analysis.
So do you mean that when it can process over 24 frames per second, then it is real time?
Might be. That is a. That is a.
I'm not sure about a specific number, but yeah.
Okay. Okay.
You can see the frame. The frame is if the frame is only 8, so it cannot be used as a video. So as long as the image is coming, you cannot prediction on real time, right?
Okay. Thanks.
Okay.
Yeah. Are there any other questions?
Yeah, I think you can raise questions. And Zhangcheng, especially you are another presenter, another paper presenter, so you can actually ask a few questions because you are the one that compromise this kind of model. Okay, maybe Aaron, if you're interested, you can still ask the questions. So this is the model kind of yeah, they will have a lot of applications for artificial intelligence. Okay, so then let's move to Zhangcheng. So Zhangcheng, you're supposed to have half an hour to finalize. I will raise questions, and my question is somehow to speed up your presentations. And yeah, Yihao actually, Zhangcheng, you can just to share the screen in the meantime. Yeah, Yihao made a very clarified definition, but sometimes I just feel that it's very clear, it's very logic, and I also believe that Yizhe simplify the details. There's even no formula there, but sometimes the mathematics expression is very powerful. But anyway, so that's a very good abstraction for the models and Jonathan, please go on. Jonathan, please go on. But I suggest that sometimes, if next time you're going to do the presentation, you can just keep the progress a bit faster. Yeah, so that'll be this is one of my comments. Yeah, but anyway, it's a nice presentation and nice slides. Okay, Jonathan, please go on.
So do I start?
Yeah, start, please.
All right. The research paper that I reviewed this week is called Adversarial Examples for Semantic Segmentation and Object Detection. So it is a research paper by 4 Chinese researchers. So one of them I think is from Tsinghua University, and the other 3 are like researchers from Microsoft. Okay, so some backgrounds. Okay, it's kind of related to the previous presentation because it uses things, it uses concepts from the previous presentation. So adversarial samples basically are samples which cause these deep networks to fail on image classification. And so this paper is mainly proposing an algorithm. So this algorithm generates a large family of adversarial samples, and it applies mainly to semantic segmentation and object detection algorithms.
Yeah. So now I'm going to raise
Yeah.
questions. So anyway, so I suppose I can raise my questions to speed up your progress. So I'm saying that now you can see just what Yizhe mentioned, that if it is for object detections compared to the traditional classifiers, it's not only to provide to specify what the object is, it also specify where the object is, right? So you can basically abstract the problem into there's a region, so there's the two coordinators to indicate where the object is, and then you're going to create what this object is, can classify the two. So if it is an attack, so if the attack is going to compromise the model, so what kind of the prediction is going to compromise? The bounding box region areas or the classification result? Or the classification result of the object?
I believe it's the classification results.
Okay, so the bounding box is still correct.
I'll explain about the bounding box later on because it actually generates a lot of more than the required. So it uses the this algorithm to generate a dense amount of bounding box around the actual bounding box.
Okay.
Yeah. So the main purpose is, I think, is for to reduce the classification accuracy. Yeah. Okay, so so I believe this part has been actually shared just now already regarding object detection and semantic segmentation, the logic and concept behind these two approaches. Okay, so adversarial attack basically means to fool the deep learning networks to wrongly classify the targets in the image. So targets in this case refers to the basically the okay, in the object detection, targets mean the boxes. So it can be the actual boxes that represent the actual object, or it can be boxes that is spread around the whole image. And for semantic segmentation, actually a target refers to each pixel on the image. Because in semantic segmentation, we actually classify each pixel as part of an object. So it actually, each of the pixel is a target for semantic segmentation. And so this research paper actually talks about applying some perturbations to each pixel on the image, such that the CNN will wrongly classify it. But on the other hand, because right now people there are a lot of existing adversarial attacks, so of course these CNN models have to adapt as well. So they have some works to reduce the effects of these adversarial attacks, and one of it is such that they use adversarial examples to train their model. So the model will be more resistant towards these attacks. Yeah.
And this technique is also called adversary training.
Yeah.
So the idea is that I'm going to using the same idea to generate adversary samples and feed into model to let the model be robust against all the adversary attack. Yeah. Please go on.
Okay, so this is just the experiment using their algorithm. So this is for semantic segmentation. So as you can see, each pixel of the image is classified as part of whatever object, like a dog or a cat. So the one above the first row is what is the actual image and is classified. So you can see the purple part is the animal and the black part is the background. So it's correctly classified. But if you look at the second row, the black and white, the one in the middle, the image is actually the perturbation image. So it's actually like adding some values to each of the pixels of the original image. So after adding these perturbations, as you can see, that it's classified such that it becomes green and pink. So the green region actually was classified as a train, and the pink region is classified as a person, which is obviously wrong because, as you can see from the photo, it's supposed to be a dog. Yeah, so this is what their algorithm has, the effect of the algorithm has on like a simple image. And also object detection means you draw a box, like boxing out the object in the image. So the same thing, the top row shows that it correctly boxes out the two dots. Okay, sorry, the three dots. Yeah, there's three dots. Then the second part is after adding the perturbations, as you can see, it somewhat confuses the CNN, and it actually
that is a very interesting phenomena. So
yeah.
my question here is that these perturbations are designated, are figured out figured out in a specific way, or just to the random perturbation.
Okay, the algorithm of how to generate the perturbation is explained later.
Okay, so anyway, so there's algorithm to generate a specific pixel, right?
Yes, correct.
Okay.
Yeah.
I see.
Okay, so I will explain the algorithm. Yeah, so basically the algorithm outputs perturbation to the original image. Yeah, so it's trying to, yeah, okay. So this is just the overall like the overall look of the algorithm. So the input is obviously you need to have an image X. You need to have a classifier. Your classifier is your CNN or RCN or whatever classifier. Okay, and then we talk about the targets just now. So the target is just like, if for semantic segmentation is each pixel in the image, and for object detection is just random boxes around the image that shows like an object. Okay, and okay, actually, let me go to the next one. Yeah, okay, so we talk about the target set. So the target set is just a set of all the targets in the image. So for example, there are n targets in the image, so it will be T1 to Tn. Okay, so a label is okay. So for example, if you want to have a set of classifications. For example, dog, cat, train, human, blah blah blah. So let's say you have a set of these classifications. So each target is supposed to link to one classification. So for example, this target is a cat, target 2 is a dog, target 3 is a human, for so on and so forth. So we actually have a label set L, which represents the actual classification for each target. So for example, T1 is a cat, so L1 will be cat. If T2 is a dog, then L2 will be a dog, and so on and so forth. So if there's n targets, there will be n labels. Yeah. Okay. So
it seems that if it's for object actions, and how this adversary, so this adversary label does not touch. This adversary label actually does not touch the region, right? So, but what you just showed just now, the region actually completely became a mess.
yes, they will choose regions because they are trying to sample a lot of targets around the actual target. So those I believe those targets are the actual classification will be the object in the actual target. Yeah. Okay, so they will filter out those boxes. They are obviously like nothing, like nothing inside. Yeah. Okay, so so the adversarial label is just a label that is wrong, that is not the correct label. So for example, if L1 is a cat, so L prime 1 will be a dog, for example. So it's just the wrong label. Yeah. That's it. So M0 is just the maximum iteration for the algorithm. So the maximum amount of time that the algorithm will run in the for loop. Yeah, so the output will be the perturbation R. So it's a matrix that shows how much value to add to the each pixel in the original image.
That makes sense.
Okay.
So what I'm interested in actually is define a loss function. As long as they have a very good loss function there, I think the object will be, I think the model will be compromised with, I think with ease. Yeah. Yeah.
Okay, so this part actually because I learned about like gradient descent and loss function like quite some time ago. So this part actually I'm supposed to read more, but I didn't really have time to read more in depth into it. But what I currently understand is so they define a loss function such that, so we talk about the F bracket something something just now, right? So the F something something just represents the network, vector classifications for the specific target. So for example, fxtn is just means that the target in image X has this classification vector. So I think FLN just means the actual the true classification based on the true label for the object, and L prime N is the wrong classification. Yeah, so as you can see, the loss function you are supposed to
I see. That's very straightforward. That would be very straightforward.
yeah, you're supposed to minimize. So you are supposed to try to reduce the accuracy of the actual label for each target in the image. Yeah. And also increase the wrong label, the wrong label confidence score. Yeah. Okay. So now we go on to the actual algorithm. So we know all the label, like what all the characters represent. So so as you can see, so basically okay, let me okay. So how do I annotate?
Annotate, you are using Zoom to annotate.
Oh, I have to use Zoom, right?
Yeah, using Zoom to annotate. You move, you hover your mouse and in the top of the screen. You hover your mouse in the top of the screen, your screen. Then it will be shoot annotation.
Yeah, I already have the annotation draw.
Okay. Okay, so you just need to pen or draw, yeah, something like that. So you need to change using a different pen.
Which one is the pen?
The second one. You click the second one. You click the second one. You click the second one. You were choosing the first option. The tilde. You're choosing the tilde icon.
Oh, tilde. Okay. Oh, okay. Okay. Good. Okay. So so yeah. So it's a while loop. So the maximum iteration is M0. So just now we define T to be the set of all the targets in the image, right? So how to generate the set of targets, we will explain it later. So just imagine you have a set of all the targets right now in TM. So TM is just the set of all the targets where you want to find out the label for each target. So at the start, TM is a full set. So so we come to this step. Okay, so so this step is what it's trying to do is it's trying to find out how many of the targets, right, actually have the correct label at this point of time. So of course our algorithm is trying to decrease the number of targets that have the correct label.
But how do it know? How does it know it is correct label? So consider this. So giving such a picture, right? So when having such a picture, so we're gonna have marked the set of objects there. Right? It's a set of objects there.
Yeah, correct. Yeah.
So the point is that there is not supposed to be so the original algorithm considers a cat, and this is dog, right?
Yeah.
So it's supposed to be take the original label as the right. You should be using the original label, right?
Yes. Okay. So at the start, of course, if your RCNN is accurate enough, like all the labels will be correctly predicted. Yeah, so because in the first iteration, you will definitely all the targets will be correctly predicted because no perturbation is added yet.
Yeah, and the line 3 is going to find the most correct, right? You're going to find the most correct labels.
Correct. Okay, so line 3, what it's trying to say is it's trying to cut away those targets that have the wrong label. So TM will be left with the targets that have the correct label. So in the first iteration, TM will still be the original TM. Yeah.
Okay.
Yeah.
I see.
Okay, so so now we go to line 4. This line.
The C actually means the class, right?
C, correct. This is the class. Okay, so F. This one is just trying to find out the matrix of the, let's say, the classification, like dog is how many percent, cat is how many percent. So argmax just means you take the highest score. So for example, the highest score is cat, like 0.9. So in this case, the classification will be a cat. So you compare it with the actual label. So if the actual label is a cat, that means this thing gives true. So the target will be added into the set. So so if it's not true, like if let's say like this thing predicts a dog and the actual label is a cat, then this target will be removed from the TM.
Yeah, so it means having successfully attacked it.
Correct. Yes, that's right. Yeah, so our purpose is to reduce the size of TM such that until if it's the best, obviously is it becomes null. Yeah. Okay, so the fourth step is something to do with gradient descent. So this part I don't really know how the calculation is done, but what they do is they do a gradient descent based on the loss function that I mentioned just now. Then they calculate the RM. So RM is just the perturbation for the whole image. Yeah, so RM is so after they get RM, they do like a normalization here. Line 5. Line 5 is to do the normalization for the RM, so it becomes R prime M. So at the start you set the total R to be 0, right? So you add the R prime M from the current iteration to the total R. Okay, that's line 6. And also so now you have the total, now you have R prime M, right? So now XM represents the original image, right? So the original image, you add the perturbation R prime M, and you will get a new so-called new image XM plus 1. So that's line 7. So now your image has added some perturbation. So your cat will have some perturbation, your dog part will have some perturbation. Your, let's say like human, let's say this is a human, then this part will be added some perturbation also. So M is just the iteration number. So now you go on to the next iteration. So the next iteration, so the same thing. Now your image has been perturbed, right? So
one of the questions I'm going to ask is that is this X is a set of images or all the images?
X is just one image.
Yes, one image, right? So it's just one image.
Correct. X is just one image. We are just looking at all the targets in one image.
Yeah, something I feel weird is that why this here is a sigma, right? Actually, you can see sometimes, for example, I'm going to erase that. I'm going to erase here. So maybe I can just maybe I redraw it all. All the other stuff here. So this is a picture, and this is original object, detect object, right? So actually, this is, suppose this is T1, this is T2, and this is T3, right? So my question is that if we want to add a perturbation to attack this target, probably we just need to ignore the rest of them, right? So why we need to care if you're calculating the sigma Tn, that means we need to target all these targets at the same time. Is right? Is that because we need to have attack efficiency? We should have attack efficiency, or we're going to there's other reason.
I think these people, the perturbation is throughout the whole image.
Yeah, the whole image. Yeah, the whole image. So okay. So anyway, but sometimes so anyway, here is optimization, right? This is future optimization goal. And there have a lot of the TN. So suppose there have an K target. So basically, when we expand this formula, so they will actually have K formula put together, right? It's 1, 2, etc. So they have a lot of formula here. So the more formulas, the more objective. Each formula is an independent object. The more object we have, the more likely we have conflict. This go a conflict, right? So I think that I'm not sure whether there's of course we can just put all this together. It's just a work, and actually it's based on the fact. So I'm thinking about if we want to compromise, for example, for this target, if we just compromise one target, I can just ignore the rest of them and to find a perturbation which changes this target. Then I just before I change, I keep the x prime. Let x0 be x prime, right? So suppose we add a random perturbation just to compromise this target. Then we can go back to x0, and in this case we can change another object to attack this target, and to change x0 to x prime prime. That might be more intuitive from my point of view. That may be more intuitive.
But I think this algorithm is trying to train a optimal R such for a specific architecture, for example, RCN.
Okay, yeah. So the goodness is that it can compromise all the targeted altogether instead of separate one.
Yes,
okay.
correct.
Yeah.
It's not for specific. It's for like the architect, like a.
Yeah, but sometimes if we want to attack the specific bounding box object, we might just need to change the loss function. Right, that's easy. Another comment here is that it only changes the classification in the algorithms, but basically we can also change the bounding box. We can use the same approach as long as we put the bounding box coordinate into the loss functions. Using the same approach, you can just squeeze or just to make a mess for the original bounding box. Okay, please go on. So what I'm interested in is how to defend this kind of attack.
How to defend this kind of attack?
Yeah.
How to defend?
Let me finish. That's how to defend is an interesting view to do this.
Yeah.
Within this technique, within this technique, maybe I'm just talking now. Ruofan and Junyang can take care. So for now, we have a lot of logos on the images. So with this kind of approach, if the tech will have our model, it can just compromise models with this perturbation. It can add some kind of pixels, random pixels in this screenshot. But anyway, it is us to take the screenshot. So somehow, if the tag is going to happen, it's going to add some random icon. Maybe to add some random icons in the pictures, or maybe to remove some kind of words, or add some other colors so that it can still do something, do this kind of attack. Actually, that's kind of interesting research. Keep going on.
Okay. Oh, joy. Okay.
Yeah, I think that's a very good research idea there. I think you have a lot of things to do now. Please go on.
Yeah. Okay. Yeah. So as explained, the output of the algorithm is R, which is the final
perturbation. Yeah, the final perturbations and attack. Yeah.
So how you're gonna create a set adversarial image is using this formula. So X is the original image, right? So you add the mean of the original image plus the R. Then you do a truncate, so you make it in a range from 2 to 0.
I have some problems. Why there's a mean of the X?
Mean of X. I think it's let me think. It's so that each of the I think it's such that R won't affect the X in a very too much, so that it still looks that it's real, I think, if I'm not wrong. So it's something like
so what does it mean? So as we discussed, X is individual image, right?
Yeah. So mean is, I think mean, it just means the mean of all the pixels added up.
All the pixels of
yeah.
what?
So X is, because X is like a matrix of pixels, right?
Yeah. X is actually an image.
Yeah.
So what is the mean of an image?
I think a mean of each image, mean of an image is just all the pixels. You add up all the pixels, then you divide by the number of pixels.
So why we need to do this?
I think it would be to like
I think you kind of. I think you just keep that questions. I think maybe you haven't got answer. So maybe you can just check the papers and just reflect it in our WeChat group. Yeah. Okay, please go on. Maybe we can finish these presentations within 10 to 15 minutes.
Okay, yeah.
Okay, we can just speed up, yeah.
Okay, so we talk about the selection of the targets, right? So for semantic segmentation, it is relatively easy because, like what I've explained just now, each target in the semantic segmentation is just each pixel in the image. So there's no selection involved. You just pick all the pixels as a target. So for object detection, target selection becomes more difficult because you actually have to choose the boxes as the target. Yeah. Okay, so the algorithm actually use like things like RPG to select the boxes. Yeah, I think RPC was explained just now as well. So welcome. Okay, so okay, I was reading about NMS just now. So according to NMS, right, it selects the boxes based on the IOU, which is the section. Yeah,
Basically, it's going to IOU is to evaluate the overlapping ratio.
correct. So if let's say like your IOU is okay, so there's a step here that says let me see calculate. Okay, so you're given like they'll give a threshold n. So if the box has a IOU that is greater than the threshold n, it will be removed from the image. So if let's say your threshold n is very small, that means like a lot of these boxes will be removed from the image because usually like as long as there's a bit of intersection, it will be removed. Yeah. So in the also for example like in this case like you can see like in the end there's only one box that remains. Right? That means like a lot of the bounding box, even if you attack it, actually it is make no sense to attack it. Correct. Yeah. So I think for this algorithm, it makes the threshold very large. So in that case, a lot of these boxes will still remain on the image. So that means if we're going to attack multiple bounding box instead of one bounding box. Correct. Yes. If we only attack one bounding box, this bounding box will just be removed. Yeah, correct. So it sets the threshold of the NMS to be very high, so that the proposals, basically the boxes are very dense. Dense in the sense that there will be a lot of boxes around the actual box that will be selected. Yeah. Okay. So yeah, like I said, so a lot of the bounding boxes are only pixels away from at least one of the selected input proposals. Yeah. Then they will do one more time of filtering. So they will keep all the positive proposals. So by positive, it means that the IOU with the closest ground truth object is greater than 0.1, and the confidence score for the corresponding ground truth class is also greater than 0.1. So this is the one more layer of filtering to keep the boxes as targets. Yeah. So the basic idea is going to select it as the most important proposal to attack. Correct. Yeah. Yeah. Okay. So yeah, that's about how they select the target. So after selecting targets, they will run the algorithm. Yeah. Okay. And then they conducted some experiment using this algorithm. So it's two parts. One is for semantic segmentation, and the other one is for object detection. So they use two values to do their experiment. One is the MIOU, and the other one is MAP. Yeah. So if there is a drop in these two values, it means that the algorithm is successful in confusing the classifier. Yeah. So that's the purpose of the algorithm, the DEC algorithm. Yeah. Another question here is that sometimes the perturbation cannot be very large, right? So suppose the perturbation is very large, the images is not an image itself. Correct. So the perturbation has to be such that it is not visible to the human eye. Yeah, if not, like humans can easily tell that it is not the correct image. Okay. Yeah. Yeah. Okay. So there are some so they run their experiment on some using some of the known frameworks for image classification. So for semantic segmentation, as you can see, they use the FCN. One is the LXNet, the other one is VGGNet. Yeah. So these two I haven't read up on it lah. So I just assume that it is an existing framework. And for object detection, they use fastest RCNN, which comprises of the ZFNet and VGGNet. So they train the models on the Pascal VOC dataset. Yeah. Okay, so they run the algorithm. Okay, so here are the results lah. So this is for segmentation. The first part is for segmentation. The second part is for object detection. So the original so for segmentation is they use MIOU.
It will be very effective, right?
Yes. So you can see that there's a drop in the there's a significant
So
drop.
the model, so that means anyway. So the deep learning model is actually huge vulnerable. It's very, very vulnerable.
Correct. Yes.
So there's somehow how to detect the models. If we deploy the model in a life critical application, so that that definitely need that is concern. Yeah.
Yes, correct. So yeah, basically the paper is trying to show that their algorithm is very effective. Yeah. Okay. Yeah.
Click it on. So can you finalize the presentation within 5 to 10 minutes?
Can, no problem. Yeah, okay. So after that, then they analyze the results. And so they talk about so we talk about just now choosing the targets, right? Using in the NMF's process, using different IOU rates. So they realize that as the IOU rates increases, which means the threshold rate increases, the MAP values actually go down even more, which means the adversarial attack is even more powerful. Yeah. So they chose a large, in the end, I think they chose a large IOU value of 0.9 for the NMS. Yeah. And so then they also talk about the maximum number of iterations. So for the algorithm, so the algorithm will stop once the target set is null or the maximum number of iterations is reached. So they run so I think it's easier to show on the graph. So so the first graph is talking about the NMS threshold. So we talked about it just now already. So the next two graphs talks about the number of iterations. So as you can see, as the number of iterations increase, there's like a decreasing decrease in the graph for the active what's it called? Yeah, so there's I think this shows the active pixels. Active pixel, I think it represents the number of targets that are still fairly in the target set.
So basically, the more we train or the more we type, the less number of pixels we can change on this part.
Correct.
So if we are just talking, so that's reasonable.
So it's showing, I think it's trying to show that around 200 iterations for the semantic segmentation and 150 iterations for the object detection, roughly the model is well trained already. Yeah. Okay, and so we talk about the perceptibility, which means how real the perturbations are. So in the sense, I think they used a formula. Okay, so in the research paper, they actually use a formula to calculate it. Okay, let me see. Okay, it's here. Yeah, they use some formula. So basically, what the formula is trying to say is they are trying to average out the
I see. So basically, I think the mode, I mean the distance, it should be smaller. So what's the threshold? What is the threshold?
Correct. So they are trying to
very small. Okay.
So they are trying to say.
I think it's not. I think this is not fair. It's not fair. Let's go back to the equation.
Okay.
The formula. So here you can see this is R is actually a matrix, right? It's actually a matrix. So K is actually the
K is just the, let me see. K is the number of pixels.
Yeah, the total number of pixels.
Yeah.
That's fine. That's fine. So what I just mean is I suppose this is the images, and R is only changes this from 0 to maybe 200. 200. So this is actually a very large change, but it might be averaged by the rest of the 8 pixels. So that is not fair. But anyway, it's the K is only calculates the change numbers. So that'll be fine. Okay.
Yeah, so I think they are trying to average it out and see whether each pixel the change is big or not. So they found the change is.
Sorry. So here I think it is just average out, right? So
yeah, they average it out.
How does it supposed to be? 10 to minus 3. how it could be this value? The only reason we ever do this value is that means that the k is extremely large. Yeah, that's not how the problem. They have some problem to about this. Yeah.
Let me see. RGB space.
RGB space. So yeah, so let's keep going on. I think this is something we need to take care of. But I think we will address kind of different problem. Yeah. So in this case, please go on. I think let's finish your talk, and then I'm going to give some comments. And there's some stuff to do in the following weeks.
Okay, so the next part of the paper talks about using the train model to attack other types of models. So the first type is cross training. That means you use the perturbation trained on a specific network with data set A. You try to attack another network with the same.
The idea is that it's going to learn the perturbation pattern and to apply so that when we have a new images, we're using this pattern to generate a new perturbation. So that without learning the other models, this kind of a patterns will be used to generate a new effective perturbation, right?
No, it's just for attack, like trying to see how well your model trains the perturbation even when your training set for the original classifier changes.
Yeah, I see. So basically, so idea is here. Now all the perturbation can be learned because the network structure is there.
Correct. Yeah.
So what if there's a new network model, which is a black box to us?
Correct. I will talk about it later. That will be the point later.
Yeah, here's the point. Yeah.
Okay. So for cross training, actually, they found that the result is not as effective as the original model, but it's still like half as effective. Yeah. Okay. So for cross network, that means you use let's say RCNN. There's a few like different types of RCNN. You use you use the perturbation train from one RCNN to attack another RCNN model. So they found that the attack is quite ineffective. Yeah. So and then they do a cross task transfer, means like they use they use the perturbation train from semantic segmentation to attack a object detection model. Then they realized that for network with the same architecture, that means like I think what they mean is if the classifier is trained using the same network, the original classifier is trained using the same network, the attack is still quite effective. Yeah,
so can I ask what network to train? What is network to train the perturbation?
Yeah, they talk about it here. Okay, let me try to find out. Okay, yeah, so this part they talk about it. If the same network, so like FCN, VGG for segmentation.
No, I'm asking is that the perturbation. You need to apply a learned perturbation, right?
Yeah, the perturbation is just a perturbation. It's just like it's just a perturbation. Yeah.
No. I'm asking this. So you mean the same image, using the same image, and the perturbation learned from the same image. If we change the model, whether the same perturbation can still work.
Yeah. Correct. Yeah, that's what it means. Yeah.
Okay, I think that seems too fine.
Perturbation is just a constant. Yeah.
Okay.
Yeah. Okay. So the conclusion of these three tests shows that the adversarial perturbation are related to the network architecture. So if you use a perturbation train on a specific network to attack another network, the attack won't be as effective.
That is reasonable. Yeah.
Correct. Yeah. So then they talk about the black box attack. So most of the time we do not know whether a specific classifier is trained using whichever frameworks out there. So they talk about how to combine the perturbations so as to perform better on the black box attack. So actually this part I didn't really read much about it because it's nearing the end. So I think it talk about like adding up all the R values, if I'm not wrong. Yeah. you talk about like you train a few different R's, then you add them up, then you attack, then you use this.
So the different R is for different architecture.
Correct. It's for different architecture. Then you add up and you attack a classifier that is unknown. Yeah. Then it proves that it's still effective. Like that's what they said. Yeah.
So as long I think the prerequisite is that one of the architecture is correct.
Yeah. That's right. Yeah.
So as long as the model actually using a very different architecture, but that makes sense. For now, I think a lot of people are using the state-of-the-art architecture like the ResNet, right? The VGGNet, so or the Google Net. So as long as we have a perturbation for all this network, so that will make sense. Okay.
Yeah. Yeah. Okay. So that's about it. So maybe I just briefly summarize. Yeah. So we talk about how they use the DAG algorithm to generate adversarial examples to attack both semantic, segmentation, and object detection networks. So they define a dense set of targets using the threshold value of NNS. Then they define a set of desired labels, means the actual labels for each of the targets. So they created a loss function and they optimize it in order to calculate the R value. So the function will output a R value for each of the networks. Yeah, so experiments show that this DAG algorithm is effective to generate visually imperceptible perturbations that can confuse the original high confidence recognition results from whichever networks. So then we also talk about the transferability of the perturbations generated by this algorithm. So it is shown to be effective between networks of the same architecture, but across different networks is ineffective. Yeah, and also we also talk about the black box attack, where we combine the perturbations from different networks to attack a model that is unknown. Yeah, so that's about it for my presentation.
Okay, I think it's a very, very wonderful presentations, and I actually enjoy the presentation a lot. So they have, and also the talk is actually the paper itself, and it's very very inspiring. And I think you also clarify a lot of the details. I think you did a very good job. So now I give my comments. So I have two questions for you to think about it. The first is that when we have such adversary attack for object detection models, how do we define it? How do we define it? How do we apply the adversary trainings, or whether we can so basically we have two clues for that. The first is that we're going to recognize all the adversary patterns, all the adversary attack patterns, but I'm not sure how that is. We need to think about it. Another is that we do the adversary training. We do the adversary trainings on so we're using a similar approach to do the adversary, so to apply the perturbations on the images. And we train, as we consider this perturbation as a special kind of data augmentation, then we're going to retrain the model to see the effect. So this is two clues. So I think you just need to have to record it and take a note for that. So that's one of the directions. Another is that for whether we can apply this kind of approach on Ruohan's model. So we do have a YOLO model, and these YOLO models actually are now going to be enhanced by Yizhe's new model. So Yizhe actually trained a pile of new models. So can we using this kind of approach to attack our model ourselves, right? To attack the model ourselves. But the note is that in our application, the challenge is that we are going to train to learn the phishing website screenshot, right? The website screenshot. The problem is that the kind our approach is a fish identifier, or is a fish detector. So for these fish detectors, it is us who take a screenshot of the web page screenshot, right? So in this case, the attacker, I mean, adversary attackers have no chance to add perturbation on our screenshot, right? So the only stuff he can do is that add some pixels on the logo, on his logo,
Yeah,
or add on the other, maybe add some icons. So this mathematic gradient descendant approach may not apply on the whole region of the image, maybe only applied on a few regions, and how we can invent a new approach to compromise our model. So that's basically you can take the notes of these 2 points. I think there's valid points and which open new research directions in the group. Yeah. Okay. Yeah. Okay. So I think it did a good job, and it's actually already 5 p.m. now. And thank all the people who still attended here. So is there anyone who has questions to Zhangcheng and me? Okay. And anyway, so I think we have